All right, welcome back. We're going to look at a few more examples of definite integrals that require the use of u substitution in the process of applying the second fundamental theorem of calculus. Because remember, to apply the second fundamental theorem of calculus, you have to know a antiderivative of the function. You have to have an antiderivative in hand. So we rely, for these three examples, on our techniques of antidifferentiation via substitution. So let's hop right in and see what we can come up with. So let's see here. The first one, notice oddly enough, is not composite. Actually, A or C are not composite functions. But remember, not all integrands that require substitution are composite. Sometimes, like A and C here, we have quotients or perhaps products that we don't have a better way of anti-differentiating. So substitution does work for lots of situations, not only composite functions. So let's see. Example A here does look a little weird in the sense that there's just a dx on top. But remember, we could easily rewrite this. If that looks weird to you, like some books would write this as I have here, dx over x natural log x. I've seen other authors do this, and put the dx right there. But I've seen plenty of folks, and myself included, who put the dx on top if there's only a 1 on the numerator otherwise. Okay. So again, this is not composite, but it's here in the definite integration that requires u substitution section. So let's see what we can do here. What might we choose for our substitution? Now remember, I usually say, hey, choose the inside function. Well, there is no inside function here, so we can't choose the inside function for our substitution u. And here is what I'm going to do. I think I'm just going to let natural log x be u. Let's see what happens. Let u equal natural log x. So that's like part of the denominator. Now, if I think that's going to work, well, then I need to immediately take the differential of u, or calculate the differential of u, and we get du equals the derivative of natural log x, that's 1 over x, times dx. And what do you notice we have here? If we do a little bit of rearranging here, I'll just rewrite the integral with just rearranging it, without doing anything substantive. Just rearranging it as 1 over natural log x, and then we have, of course, 1 over x of dx. That's the same thing, right? All I did was write it as the product of two fractions instead of a single fraction. And here is exactly what we have is du, and here is u. So, actually, sorry, that's a 1 over u, rather, not u. Sorry, so I should say, I should only circle that. There's u. Okay, so now I'm ready to change over to my new variable, and let's see what that does for us. Now remember, we can't forget to change over our limits of integration. So I'm going to leave those blank for right now, and then just substitute. Okay, natural log x, that's u, and then 1 over x dx is du. So I get this. Integrand, and now, okay, I need to consider my limits of integration. So I have the substitution u equals natural log x. Okay, so if my original lower bound x was e, then the corresponding value of u is when you plug in an e. So u equals natural log of e, and now what's natural log of e? Remember, e is the base of the natural logarithm, and e the x and natural log x are inverse functions, so this is simply equal to 1. This is asking us e raised to what power gives you e? Well, e raised to the first power gives you e. So my new lower bound of integration, lower limit of integration, is 1. What about the upper bound? My original upper limit of integration was e squared. So if x equal e squared, then u equals natural log of e squared. Okay, and again, like I mentioned a few moments ago, these are inverse functions of each other. So this automatically, by the inverse property of logarithms, reduces to 2. Or you can think about it as this is asking us literally, the base here is e, the base of the natural log is e, so this is asking e raised to what power gives you e squared? Well, clearly, if you think about it that way, 2 is the answer. So my new upper limit of integration is 2. And so now I have my brand new integral that I have the integral from 1 to 2 of 1 over u du. Interesting. And now what can I do with that? What do I know that I have, what function do I know that's in my derivative list that is the result when I differentiate? Well, remember, we know that the derivative with respect to x of natural log x equals 1 over x. And so if we have 1 over the variable, then we use natural log for the antiderivative. Now, there is that one caveat that in order to make the domains work appropriately, we have to use absolute value when we antidifferentiate. So we have to say that the antiderivative of 1 over x dx is natural log absolute value of x plus c. Now, of course, we can forget the plus c here because this is a definite integral. But we anti-differentiate regardless, and we get a natural log absolute value of u from 1 to 2. Okay? And then we apply this right here means we're about to apply the fundamental theorem. And so, of course, in the next step, we do apply the fundamental theorem. And we first substitute in 2, so we have natural log absolute value of 2 minus natural log absolute value of 1. Just to remind you, this is capital F, the antiderivative, evaluated at b, and that is capital F, the antiderivative, evaluated at a. So that's capital F minus capital F of b minus capital F of a. Now, a lot of times when you use, not always, but a lot of times whenever we use natural log in this process, of course we have the absolute value. But if you're plugging in a positive, a non-negative number into this expression, well, then the absolute value doesn't really matter. So we can only ignore the absolute value because 1 and 2 are already non-negative. So this is the exact same thing as natural log of 2 minus natural log of 1. Now, what's natural log of 1? Now, that does reduce to a nice number because this is asking us e raised to what power gives us 1? Well, e to the 0th power gives us 1. So natural log of 1 is 0. This simplifies, therefore, to natural log of 2 minus 0, or natural log of 2. So, natural log of 2 is the area, or as I should say net area, because I'm not sure if this region is non-negative from et squared. We'll look at the graph once we're done with all three. But the net area is what we'll be safe with saying right now is natural log of 2. Natural log of 2 is what? I mean, okay, that's like saying e raised to what power gives you 2, but e is bigger than 2. It's 2.78. So that's a number smaller than 1, we can say. Okay. Now let's look at example B. Example B is actually very similar to an example we did in the text a little while ago. The written example I provided in the text. But here, it's not just 5z plus 1. There's a quotient involved. So it's going to actually, although it looks kind of superficially the same, it's still a radical of z squared plus 1. Here, I'll just show you. Just to remind your memory, just to refresh your memory, we did a radical 5x plus 1, but there was no quotient involved, and more importantly, there was no variable on the numerator. So anyway, it looks superficially the same, but I think, I don't know. We'll see how it works out. I think it's going to require a different approach. Although, substitution, generally speaking, but that z on the top is really going to throw things off. Okay, but let's just see what happens. I think, since this is a composite function, we can use our usual guess of the inside function being our substitution for u. So let's say let u equal 5z plus 1. And then, so we're going to immediately then calculate du, the differential, is what? 5 is the derivative times dz. Okay? So let's see what we can do now. So we can say, let's just start off with the definite integral from 0 to 3, the original. A z up top, and a radical 5 z plus 1 on the denominator, dz. Now, if we try to immediately apply our substitution, what happens? So on the denominator, well, that's nice because it just reduces to a square root u. That works out well. But notice on the numerator, I have z dz. Ooh, yikes! I want to. Well, if I have a 5 dz, so I have to change over the dz. Like, that's not a choice. Like, I have to have a du somehow. So I need in order to change over to a du, I need a 5 dz. So I'm going to have to apply the constant multiple rule, which says, hey, if I put a 1 out front, if I multiply the integral by 1, that is 5 over 5. Okay, well, I can break that apart and say that's the same thing as 1/5 times 5. That's still multiplying by 1. And then I can use the constant multiple to bring in a 5, so I get a 5 dz. So I'm going to just erase that 5 right there, use the constant multiple rule to put it right there. And again, this is all just multiplied on the top. So basically, I have a 5 dz on the numerator now, and I know I can replace that with a du. So I can do that, which I have to have because I'm changing over completely to the variable u. But here's a pesky problem, and we've seen a similar situation back when we were just doing anti-differentiation via substitution, without knowing about definite integrals yet. We saw the similar situation where, hey, I did my substitution, but now I still have this annoying x, or in this case a z, left over. And what did we do? Well, in a case like this, we went back to our original substitution and rearranged it to solve for, in this case, z. So if we chose our original substitution is u, we can rearrange that and solve for z. If we say what? If we subtract 1 from both sides, we get u minus 1, and then divide by 5, we would get u minus 1 over 5 equals z. Now, we know that equals a z, and so we can substitute in. Now, you're going to think I'm crazy because you're going to say, well, this does not look any better at all. You're going to say, probably it looks worse. Because now we're going to have, let's see, u minus 1 over 5 divided by the square root of u. So now we have a compound fraction. Okay, yes, you'd be right to think, okay, immediately that doesn't look very good. But I think we can work with this. Okay, we have a fraction, and we can think about this. Divided by a fraction, so what do? You flip the divisor and multiply. So we're going to end up getting something like this. U minus 1 with a 5 and a square root of u on the bottom, like so. Now, I forgot to update my limits of integration. I left them blank there, which is good. And by the way, I forgot to bring along my 1/5 out front. Kind of getting ahead of myself here. Let's talk about the limits of integration. So my original substitution is u equals 5z plus 1. So I need to use this to update my limits of integration. So my original lower limit was 0. So if x equals 0, then u equals 5 times 0 plus 1. So you just get 1. So my new lower limit of integration is a 1. So I put that in both places. And then my original upper limit of integration was x equal 3. Oh, you know what? I used x's. Sorry. Those are these z's. You might not have even noticed. So if z equals 0, so the original is if z equals 3, then u equals 5 times 3 plus 1 is 16. So those are the same that, since we have the same substitution that we used a little while ago in that previous example, and the same upper and lower starting upper and lower bound, well, we have the same upper and lower bound of the transformed function. So we get a 16. Okay? Alrighty, now let's see what we can come up with. Let's see what we can come up with. So we changed our limits of integration. Now do notice we need to do a little bit of algebra here. We've worked with stuff like that before. We've anti-differentiated integrands like that before, but it took a little bit of algebra before we could get it into the right form. Now, before we do that, I need us to recognize also this fact, that u minus 1 over 5 square roots of u, that's the exact same thing as u minus 1 over the square root of u times 1 over 5. That is, dividing by 5 is the same thing as multiplying by 1/5. Now, why is that important? Because if I think about multiplying by 1 over 5, I can see it's a constant multiple, and I can factor it out. So I already have a 1/5 out there to start with. That came from my original strategic multiplication by 1, but now I'm going to have another 1/5 out there. So I'm going to have a 1/5 times 1/5, which we'll update on the next line to simplify it. But now I'm going to have u minus 1, and by the way, I'm going to write this as u to the 1/2 power instead of the square root of u, because that's what we always do when we're working with either derivatives or anti-derivatives of radicals. Okay, and now I'm gonna update the leading coefficient here. It's 1 over 5 times 1 over 5. That's 1 over 25, and then I have the definite integral from 1 to 16. And now let's do the algebra. In fact, let's do the algebra off to the side. Here, let's do this. So I have u minus 1 over u to the 1/2. I can break that apart into two fractions, and that gives me u divided by u to the 1/2 minus 1 over u to the 1/2. Okay, now what about properties of exponents? For this first term, I have u to the first power, it's understood first power, over u to the 1/2. Now the properties of exponents, the quotient property specifically, says if you have the same base expression on the top and the bottom of the quotient, well, you can combine that into a single term of that single base, and you subtract the exponents. So what's 1 minus 1/2? Well, it's 1/2. And then we have what? If we want to write this without the u on the bottom, we want to move it to the top so we can use the power rule for antiderivatives. We just write that as u to the negative 1/2. Okay, so now I can replace this expression, this single fraction, the single quotient, with two power functions, u to the 1/2 minus u to the negative 1/2 du. And now I am on my way, because I have two functions that I can easily anti-differentiate using the power rule for anti-differentiation. So what do? We first of all open the parenthesis here because we have two terms. So we open a parenthesis, and then we say, all right, we increase the power of that first term by 1. So you get u to the 1/2 plus 1, and then you divide by that same new power, minus, and we do the exact same power rule. We increase the power by 1, so it's negative 1/2 plus 1, divided by negative 1/2 plus 1. And we don't have to worry about the plus c because this is a definite integral, and we are about to evaluate this using the fundamental theorem of calculus part 2 at 16 and 1. Now let's just clean this up a little bit, okay? Because it is a little messy right now. So we have u to the 1/2 plus 1. That's u to the 3/2 power. Okay, and we're also dividing by 3/2. But dividing by 3/2 is the exact same thing as multiplying by 2/3. Dividing by 3/2 is the same thing as multiplying by 2/3. Minus, okay, now we have u to the negative 1/2 plus 1. Okay, well, negative 1/2 plus 1, that's positive 1/2. So we have u to the 1/2 power divided by 1/2. Well, dividing by 1/2 is the same thing as multiplying by 2 over 1, or it's multiplying by 2. And then we're going to evaluate at 1 and 16 in just a sec. We're going to apply the fundamental theorem. Okay, and now it's just a matter of doing just that. Now we do have like a 1 out, so we have a 1 out of 25th out front, and then 2 terms with subtraction. So we got to be careful here when we apply the fundamental theorem, because there's a lot of room for arithmetic errors. Let's be careful here. 1 over 25. I'm going to open a set of brackets. Okay? Because that 1 over 25 needs to apply to this entire thing. Now, let's evaluate capital F of B, which is capital F of 16. So it's 2/3 times 16 to the 3/2 power minus 2 times 16 to the 1/2 power. So that, my friends, is capital F of B. Minus, and again, use parentheses. Now we need to do capital F of A, which is 1. So we have, which is when we plug in a 1. So 2/3 times 1 to the 3/2 power minus 2 times 1 to the 1/2 power. And now I need to close my brackets, again, because that 1 over 25 applies to everything, and that is capital F of A. So that is my application of the fundamental theorem of calculus part 2. Capital F of B minus capital F of A. Okay, and now let's see what this arithmetic does for us. Of course, we have that 1 over 25 out front. Now, let's see. 16 to the 3/2 power, don't let that scare you. It's just saying take the square root, then cube the answer. So what is the square root of 16? Well, it's 4. What's 4 cubed? Well, 4 cubed is 4 times 4 times 4 is 64. Okay, and then we have, what, 64 times 2/3. So let's just see, 64 times 2 divided by 3 gives us, in a fraction, it's 128 over 3. So 128 over 3 minus, 2 times 16 to the 1/2 power, that's the square of 16 times 2. So what, 4 times 2, so minus 8. Minus, now 2/3 times 1 to the 3/2 power, 1 to the 3/2 power is just 1. So we have 2/3 times 1, or just 2/3. Minus, the square root of 1 is 1, so minus 2. And at this point, I think I'll just grab my calculator and do this. So, of course, you could just get a common denominator and do the arithmetic if you really wanted to by hand. But for the sake of time, I'll just do it in my calculator. So we have 128 divided by 3 minus 8. Now be careful to distribute. Actually, be careful to distribute. This negative goes there and makes it that a negative and makes that a positive. Or alternatively, I'll do this to show it. The first fraction here, 128 over 3 minus 8, that is 104 over 3. So we get 104 over 3 for this first set of parentheses minus. Now what's 2 over 3 minus 2? That's negative 1 1/3, so negative 4/3. So minus negative 4/3, like so. And now we will get 1 over 25 times what? We have 1 over 4 divided by 3 minus a negative 4 over 3. So they have a double negative, so that's going to be what? 108 over 3 because of a double negative. Divide by 25, let's see what we come up with. Let's see, 108 over 3, and we're going to divide by 25. Does that reduce at all? Yeah, it does. Nice. 36 over 25. Okay? Again, I don't know if that's net area. Well, of course it's net area. I'm not sure if we can go further and say it's area because I don't know if this function is non-negative. Actually, it is non-negative. Why? Because I know the denominator is always positive. It's a square root. The numerator would be 0 when z equals 0. And if you're plugging in a positive, think about between 0 and 3, you're plugging in positive values for x. so the numerator has to be positive, and the denominator is always positive. So yeah, that function's non-negative, even without knowing what the precise graph looks like. So we can say that answer, 36 over 25, is indeed area, since the function, the integrand, is non-negative over 0 to 3. All right, last one. The last one of the trifecta here. Arctan. We don't usually deal with inverse trig every example, and you guys tend not to like inverse trig, but inverse trig is very useful, especially for you folks going to Calc 2. So, I mentioned it at the onset of this video that this is not a compound integrand here. Sorry, not compound, composite integrand. Arctan divided by 1 plus x squared. Well, that's just a quotient. Okay, so the question is, what do you make for your substitution? Well, do you notice anything about the relationship between arctan and 1 plus x squared? Here's my hint to you. The derivative with respect to x of arctan x is what? 1 over 1 plus x squared. So do you see where we might be going with this? What do we literally have? If we separate here, I'll separate it for you. If we separate this out, we have the definite integral from -1 to radical 3. We literally have arctan x rather, times the derivative of arctan. We literally have a function times its derivative. And isn't exactly that what we want if we want to recognize like that we need to undo the chain rule? The chain rule gives us a function times its derivative. Okay? For a special case. Okay? So let's just think here what we have here. What we do here. What if we let arctan be u? Let arctan be u. We let u equal arctan, then what's du? Okay, well we just said the derivative of arctan is 1 over 1 plus x squared, and since we're calculating a differential, of course we put the dx on the side. And notice that's exactly what we have. We have du right here, and we have u right here. So this one, although it looks weird, it immediately works perfectly for u substitution. Perfectly. I mean, I admit it looks weird, but it works out perfectly for us. So now we can immediately say this is the definite integral. Well, we have u du. So that simplifies crazy nice from a quotient with inverse trig and a polynomial in the denominator to u du. And that's the beauty of anti-differentiation via substitution. Now, we do have to update the limits of integration, however. Okay, so let's see here off to the side. If the original lower limit x equals -1, then u, well, we plug u into our substitution arctan. So arctan -1. All right, you tell me. What's arctan -1? Now remember, with arctan, you're basically asking yourself this question. You're asking yourself the question, tan of what angle gives us -1? And remember, because tangent is not 1-to-1 by default. Tangent, is lots of curves. Oh, that's terrible, but kind of like, oh, that's even worse. Let's start that over. Undo. Tangent is, I'll go a little slower. Lots of curves that kind of look like that. I'm not a very good artist here, but lots of curves like that. Clearly that's not 1-to-1, so clearly it's not invertible everywhere. However, if we restrict our domain to only talking about, well, You don't restrict our domain that much. Let's restrict our domain that much. And so we only talk about like one little slice of arctan. And where is that one little slice? Between pi over 2 and negative pi over 2. Well, now the function is 1 to 1. My point of saying that is the angle, our solution here for arctan negative 1, it needs to be between negative pi over 2 and pi over 2. So think about your unit circle. Tangent is the ratio of two sides of a triangle. So you're asking yourself, where do I have a ratio of two sides of a triangle? And by the way, I'm only focused on the right half of my unit circle here because I'm concerned between negative 2 and positive 2. So where between negative 2 and positive 2 is the ratio of the x and y coordinate negative 1? Well, I think the only possibilities for getting a 1 or a negative 1 would be like right here and right here, right? Because at that point you have radical 2 over 2 comma radical 2 over 2. And what do you see? The ratio of the two sides of the x and the y coordinate is 1. Now we want negative 1, so that's not going to work. So what about down here? Well, down here we have the ratio is what? The coordinates are root 2 over 2 comma negative root 2 over 2. Okay, and if you take the ratio of the x and the y coordinate, yeah, you get negative 1. Now, what is that angle? Now, we're only focused on solutions between negative pi over 2 and pi over 2. So, although there's lots of different things you could call this angle, you could call it what? That's 7 pi over 4. But 7 pi over 4 is not between negative pi over 2 and pi over 2. Instead, we need to call it this angle, the coterminal value, which is negative pi over 4. Negative pi over 4. This would be positive pi over 4. This is negative pi over 4. Okay? So, arctan of negative 1 is negative pi over 4. Okay? So, that's going to be our new lower limit of integration, negative pi 4. Now, what about the upper limit? So, instead of now tan of question mark equals negative 1, we have tan of question mark equals radical 3. But we basically need to ask ourselves the same question. What angle do we have over here where if you take the ratio of the x and y coordinates, you get radical 3. Well, hopefully radical 3 kind of rings some bells because, we do have radical 3's involved on our unit circle. So let's see. Like, for instance, we have, like, right here, we have the coordinates, what? 1/2 comma radical 3 over 2. And then right here, we have the coordinates radical 3 over 2 comma 1/2. So remember, tangent is the y coordinate divided by the x coordinate. So which one of those, if you take the ratio, gives us a radical 3? Well, you take the tangent, sine over cosine. So you take the y coordinate, like for instance right here, if we took the y coordinate, you'd have radical 3 over 2 divided by 1/2. Now what do you get if you do that? Well, if you flip and multiply, you get radical 3 over 2 times 2. So you get radical 3. Now, so what's that angle? That angle is what? Pi over 3? Pi over 3. And so we get our new upper limit, our updated upper limit is going to be pi over 3. So we could say if x equals radical 3, then u equal arctan of radical 3. Oh, that's a very bad radical 3. And radical 3 equals pi over 3. And again, you got to be on top of your unit circle and your inverse function business. You got to be on top of that to get that updated upper limit of integration. Okay, so we have pi over 3. Now what can we do? Well, after this, it's a very easy task. Okay, so we have pi over 3 goes right there. That's a very easy task. Why? Because all we have to do, all that's left to do is anti-differentiation and then applying the fundamental theorem part 2. And by the way, we just have the integrand is a u. So it has a super easy antiderivative. It's u squared over 2. And we're going to evaluate from negative pi over 4, pi over 3. Okay, I would probably write this as a 1/2 out front. I like to do that. You know, division by 2 is like multiply by 1/2. And then I'll open up a set of parentheses like so, and we'll have just u squared. So it'll be pi over 3 squared minus negative pi over 4 squared, like so. Again, I factored a 2 out, a 1/2 out, instead of having a, if I didn't do that, basically I'd have a compound fraction, and I like to avoid compound fractions. Okay, so let's see what we get here. We get 1/2 out front, of course, then we have pi squared over 9. Now we have minus, okay, so minus now, negative pi over 4 squared is a positive value, so it's positive pi squared over 16, but you know that negative between them stays because, again, when we square a negative number, we get a positive value. Okay, so this equals 1/2. All right, I guess we need a common denominator. What's the common denominator here going to be? I guess we could do 9 times 16. What is 9 times 16? 144. So let's just do that. It'll simplify out if in the end if we end up getting if there was a better choice for a common denominator. So it doesn't really matter. We can get a common denominator. It doesn't have to be the least common denominator. So let's do 144. And then if we, to do that, we would need to multiply this left fraction by 16 over 16. So that's going to give us 16 pi squared. And if we, to get the common denominator, we multiply the right fraction by 9 over 9. So minus 9 pi squared. Okay, so that gives us a 1/2. Now 16 minus 9 is 7. So that gives us times 7 pi squared over 144. Okay, and then if we multiply by 1/2, same thing as dividing by 2. I think that gives us 7 pi squared over, what's 144 times 2? What, 288? So divided by 288. Now it's possible that simplifies. Let's see. 7 divided by 288. I'm not sure. Does it simplify? Nope. Nope. So there we go. Nice. What is that approximately? It's approximately, what, 7 pi squared divided by 288. It's approximately like 0.23. So let's make sure that just makes general sense when we look at the graph in just a moment. That the net area is about actually 0.24 if we round to 2 places. About 0.24. Okay, again, I have no idea what that graph looks like. Arctan over 1 plus x squared, I have no idea. All right, let's pull Desmos up, see what we can come up with. So with this first one, going back to A, we have, well, 1 divided by x natural log of x. So there's the graph of the original integrand. Now we're only concerned from e less than equal to x less than equal to e squared. So we're only concerned with that little portion there, okay? And remember, we're only concerned with the portion that's between the x-axis and that curve. So y less than, and let's then do this, y is also greater than 0. So this is the region we're concerned with. We're trying to find the area of that. Clearly, that shape, we don't have a usual geometric formula, so we're stuck with calculus. Now, what did we do? Now, what we did was we transformed that into 1 over u. So we transformed that into, we'll say 1 over x, because that's what Desmos required. And now we're focused on from 1 to 2. Okay, so instead of from e to e squared, we're focused on from 1 to 2. Those were our updated limits of integration. Okay, Oh, let's see. Why is it giving me an error? Try adding an equal sign. So y less than equals. Oh, there we go. Sorry. All right. So what we've done here is in this, and again, this is the cool thing about definite integration by substitution is this. When we make a substitution, we're saying to ourselves, we want the net area, or in this case, the area because it's non-negative, we want the area of the original red. But in that form, we don't have a good way to obtain that area. So we transform it to the blue region. And it just so happens the blue 1 over u du has a nice antiderivative that allows us to obtain that area. The beauty is they both have the same net area, or in this case, they both have the same area. They both have the same definite integral. So although we're going from e to e squared, and it's like a shorter, kind of skinnier, longer red region than the blue, which is kind of taller and more square, they have the same area because these are non-negative functions. So that's super cool to me. I hope it's cool to you. Let's look at the middle one. We have, let's see, it's x, well, we're going to translate to x's instead of z's. So it's x over the radical square root of 5x plus 1. Now, we were concerned from 0 to 3. So that's the original function that we were focused on with example B. Again, a weird shape. Geometry not going to help us, so we're stuck with calculus. But we transformed that into what? We transformed that, look on line 1, 2, 3, oh, line 3, actually line 1, 2, 3, 4, 5 is right before we anti-differentiated. So there was a 1 over 25 out front times x to the 1/2 power, so that's square root of x, minus x to the negative 1/2 power. That looks good, and now we're focused from 1 to 16 though instead. All right, so that's kind of a crazy one. Look there. So the original was the red. Okay, the original was the red. But in its current form, which was z over radical 5z plus 1, we were kind of stuck. We didn't have a good way to find the area via the fundamental theorem part 2. However, when we made our substitution, we then got this new function over here, the blue function, over the domain 1 to 16. So it's a really long, skinny domain, really short, long, skinny domain. But it turns out those regions have the exact same, in this case, area because the functions are non-negative. Okay, they have the exact same definite integral. Super cool, super cool. All right, last one. Let's see what happens with the last one. So we started off with, I really have no idea what this graph looks like. It's arc tan x over 1 plus x squared. 1 plus x squared. And we were focused on negative 1 to radical 3, square root of 3. Okay, so there we are, red. That's what we originally were focused on, that little bitty region. Now we transformed it into a very, very simple function. U. Look on line 2 here. U du. In other words, just x. Okay, but we're only focused on. So that's the graph of x. It's just here. If you delete the the domain restriction, x is just a line going up 45 degrees. Okay, so it's a very simple function. But we're concerned about the region between what? Negative pi over 4 and pi over 3. Between negative pi over 4 and pi over 3. Okay? Oh, and I need to delete that restriction. Okay, so we have to go from 0 because, okay, this function is not non-negative. Negative pi over 4 obviously is to the left of the origin. So we're going to have to update this a little bit. So bear with me for just a sec. We're going to have to go from do this do this. And then do this. And now we'll have y is less than or equal to x. Okay, so let's see. Let's see here. So what do we have here? We have a function. The red was the original from -1. Oh, you know what? And I'm missing part of the original. Sorry about that, because the original is not non-negative also. Sorry. I was about to say, this answer does not look right to me, so we're going to have to do a little investigating. But it turns out my picture's not right. Here, let me fix the original red. So we have from -1 to 0, y has to be less than 0, and then fix this over here. There we go. So there's the original red region. Sorry, I missed the part that was below the x-axis. So notice that function is not non-negative. Okay, it's not non-negative. So here the interpretation is going to be net area. Okay, so of course, you know, region above, the area of the region above minus the area of the region below, and that's why we get a pretty small answer. Our answer is like approximately 0.24, and that makes sense to me because there's a lot of cancellation, because it looks to me like basically this region up to +1 is going to cancel itself out. They look to me like they're identical. This looks to me like it's going to be odd. Okay? And then so what's left over is just this little region over here, which I think has a net area of about 0.24. So that's the original, which we didn't have a good way to work with. But then we transformed to just a regular old nice identity function, y equals x, and we could easily anti-differentiate that, but we updated our bounds, and we're now going from -π/4 to π/3. So notice here with this blue function, again, it's an odd function, and so from -π/4 to +π/4, that integral is going to be 0, and then what we're left with basically is the net part, the leftover part, is just from π/4 to π/3. From π/4 to π/3. Cool. Interesting. So that is a that's it for us. You know, again, the reason I'm pulling these pictures up for you is I think it's crazy, and it's this, you know, beauty of mathematics that we have this situation where, okay, we can't really work with the original situation, red, but then we transform to a different situation, blue, via properties of algebra. Really no calculus in the substitution. It's just algebra is the process of substitution. But via algebra, now we can solve, you know, our calculus problem because of that substitution. Okay? Again, I think that's super cool. I hope you think it's super cool also. 3 more examples in the books. We'll do 1 more set of examples in the next video, and then we'll move on to a new topic. So I'll catch you in the next video looking at some more integration, definite integration via substitution. And if you have any questions in the meantime, always feel free to reach out. I'll see you then.